Testing, testing. 1, 2, 3. All right. I did it. I did it. I pressed the button on time to start streaming. Oh, that's so nice. Okay. I did that. I got my promo going. I'm feeling pretty good. Oh wait, I need to add an image. Oh wait, no, I didn't get it right on time. Oh no. I'm still struggling. Ah, I thought I had everything together. Mistakes were made. Okay. Let's see. Boom. Well, at least I got that going. So bear with me while I try to once again get things all together. Did it work? It worked. Alright, there it is. And oh, I forgot to put on my face. It's already like half point. Ugh. Good thing I got a whole 3 minutes to sort this mess out. Okay, alright. Almost there. Okay. Okay. Alright. I got the word out. I got the stream starting. I got the music. Do I have the thing loaded? Kind of. There's going to be a little bit of flickering to start with as I alt-tab. So, sorry about that. Yeah, even though it's the load up time, load up blah blah blah, time, load up time. I try not to let there be too much dead air. So, don't mind me while I just ramble a little bit. I have good news and I have bad news. But I'll wait until this. Wait. Oh shoot! I missed something. No, I didn't. I'm okay. I'm okay. Is it gonna load the right thing? Okay, and we're live. There it is. Alright, so I have good news and I have bad news. The good news is the person that I was tutoring regularly basically graduated from tutoring. They're getting help. Things are looking up for them. So, yeah. Bad news is I don't have anyone to tutor now. But that's fine. I guess that opens up my schedule once again. So, there it is. And as always, if anyone wants tutoring for whatever math that they're working on for now, yeah, please feel free to say so in the chat, and we'll work on that. But until then, I'm going to try to ramble on about the unit circle. Now, ideally, right, a lot of these categories would be of what I cover would maybe line up with the school year, right? But that I don't know. I feel like that's maybe doing things a bit wrong, because when you have like the school calendar year, right? You got month after month after month, and you're covering subject A, B, and C in like a math thing, and it kind of builds on it, right? First, like generic example, you work on addition, then you work on like multiplication, and then you work on something like exponents, right? Because they build off of each other over a period of time. But when it comes to like tutoring someone, they're usually not working on like the latest and greatest thing, and you know that's where they're struggling. Usually it's like a lesson 1 or 2 behind, and that's where they need the help. So even if I did have a schedule that I followed along with the school year, it would be nice, but I recognize that that might not be exactly what people need. Maybe they need help with something that they're supposed to learn like weeks ago or last semester. And hey, that's just how it is. So hopefully, if you're in that boat, you know, speak out, get help. It's never too late. There's always time to learn. But until then, for now, I'm gonna be jumping onto something about unit circles. So again, forgive the flickering. It's gonna kind of go on and off as I Alt-Tab between these things and try to get screenshots. Wow. Okay. Does this work? Copy. Paste. Lovely. Alright. I'm gonna scoot my head by scooting the board, and here we go. So, unit circles are basically a circle on the XY axis. So before we get into kind of, you know, reading verbatim what's there, what's a good spot? Ah, here's a good spot. Sure, why not? First you have the x-axis, which at some point, I don't know, again, how far people are into whatever math that they're into, but the x-axis would be from one point to another, right? So usually when you learn about this, it could be something like distance. So if you're visiting a friend's house and you're going from point A to point B, and you got to figure out, you know, how many miles is that? Again, it's not like an accurate representation, because, you know, maybe you got to go like this way on the freeway, and then you got to, you know, take these roads over here, and then, you know, you got to go through this other entrance, and that's how you get to that person's house, right? But in terms of math, when it comes to like applying math to the real life, sometimes they have things like simple or as a representation. So for this example, from getting a friend's house from point A to B, that would be on a line, and this would be also known as maybe like a line graph. Wait, no. I might be using that term wrong. But it would be a point on a line that you go from one to another. Say, for example, you start here, and then, I don't know, like 20 miles. And then as you move into other more advanced math, then you would go into something where you would include a y-axis. And a y-axis is where you basically go from 1D, one dimension, to 2 dimensions, right? And so with 2 dimensions, then you can have something like a function where it might more accurately graph the distance between things. So instead of just having it as like point A to B is 20 miles, maybe we would say something like point A to B is a function of x, where it actually follows along the pattern of where you're actually driving, which is pretty cool. And a lot of things involve functions like that, not necessarily for you know, personal use. I think using a map and or a GPS or some kind of map app on a mobile device is much more practical for trying to figure out, all right, you know, how far do I need to travel? How long do I need to plan for it to be from point A to point B? But before that, before the apps, before all this, there's the map, and before the map, you know, there's kind of guesstimates, and at some point in the middle, there's functions to kind of figure out, you know, going from point A to B at certain speeds. I'm rambling a bit. My apologies. But the point is that they have a practical purpose, right? Now we're going to kind of pause here at the X and Y graph, because this is where unit circles kind of come in as their own special thing. you're not going to go into 3-dimension where there's Z, and then all of a sudden you get these cool shapes, and then that's more like I don't know, what's like a modern thing that people use? I guess like modeling, like art models that you would do, and like a program like Blender, or maybe 3D printing, maybe. But that's where you do the 3rd dimension. Just for 2D, though, you can think of this as like the difference between working with Play-Doh or clay, I guess, and then and 2D is working with drawing on paper. All right, and for here specifically, I'm gonna erase a bit. The unit circle is to figure out degrees in which something is in a circular shape. I know, very, very descriptive. Absolutely not generic. But what they do is that they kind of have things. Well, first, let's go over quadrants, right? Now, why would they have the quadrants in this order where it's 1, 2, 3, and 4? And it might seem fairly arbitrary, right? And it kind of is. Because if you think about it, you know, a circle's a circle. You could rotate the thing. You could go like 1, 2, 3, 4 if you're reading left to right. Or you could go 1, 2, 3, 4 if you want to touch all the sides in the area of a circle, right? Or go in a circular pattern. But the reason why they start with a 1 on the top right side is because when it comes to X and Y graphs, this is the first side that has everything all positive. So if you have, let's say, numbers on here, right? I'm just going to go with the number 1. Because unit circles, as it turns out, they're very nice and simple in a way, because they all use the number 1. It's 1 all the way around. So it is positive 1 on this side, or positive 1 for the X. Up here, it is also 1. So this point would be looking like that. And I'll get to this notation in a bit. But then over here on this side, for the X axis, it is negative 1. So if this is 0 in the middle, going over here is positive 1, going up here to Y is also positive 1, but going backwards is a negative 1x. And then going down to here to this point is a negative 1y. And so you're going from negatives, or so positives to negatives. So the one where the quadrant, the area in which everything is all positive and kind of working nicely together, is right here. So that's why this is number 1. Now as for number 2, I feel like it could have gone either way, right? Maybe it could have gone this way, which it does. Maybe it could have gone this way, which why not? If you, let's see, in a clock that we have, where it's like, was it 12? No wait. 3, 6, 9, right? Clockwise is this way, right? But the difference is that with clockwise, you're not actually starting from this point right here at the 3. You usually start at the 12, and then you work from the top this direction. So in order for this to work, if we wanted it this way, which it doesn't work, then it would be like this weird kind of funky unit circle where it starts on the top and then your degrees kind of go this way. But that's, again, in relation to something like maybe a clock, which it does not work. So if you're thinking, well, unit circle is kind of like a clock, try to think the opposite, right? Because it actually goes counterclockwise, where it actually circles the other way, where it goes 2. I should do these in Roman numerals. 1, 2, 3. And 4. And as you can see here, nice little diagram. You start at here. 0 is not at the y, like a clock would be. It is actually on the x-axis. And then it goes to the y-axis, and that completes the first quadrant. Then it goes to the second, the third, and the fourth, and it just kind of counts all the way around. Now, maybe you might ask why. I'm sure there's a very good reason. I forgot. I know there's an exacting historical reference and reason as to why the unit circle is the way it is, why it shapes the way it is. I just know it's not based off the American clock. Which makes sense, because unit circle is much older than that, I believe. Although, I don't know, yeah. But a good way to understand it is that you're moving from positive value to positive value. So positive x to positive y, and then you're keeping the y positives, then you move to negative x. Because with any point, what's a good example here? This one's nice and clean. Okay. So with any point in the first quadrant, all these points are either positive x or positive y. There is not a single or I guess 0, but there's not a single point in here that is like negative x or negative y. And within the second area, all the points are either some mix of negative x and positive y. Because x is negative all the way over here, and y is still positive. And then I'm just going to do this for completion's sake, but I think maybe you could recognize the pattern. Here, it goes negative x, negative y. And then here you go, positive x, negative y. So if someone ever gives you like a point on a chart and they say, okay, within what quadrant is negative 4, positive 5? Right? Then you'd say, okay, the x-axis is negative, so it's going to be one of these two. And the y-axis is positive, so it's going to be up here. You connect the dots, and it's going to be in the second quadrant. Cool. Alright, now again, not quite unit circle stuff yet. Kind of more like just how the graph works. But to go more into the unit circle, the way it works is it works in degrees rather than in like, how to put it? It works in degrees and radians, not exactly like numbers and points. So before, when we talk about, well, it's functions after this or before this? I think functions come after this. Yeah, I think I jumped backwards. So things like functions and points on a dot come first. But here we're talking about unit circle. Okay, right. Gotta stay focused. Now, the nice thing is that when it comes to this unit circle, the degrees are kind of these nice shapes. And they are shapes like a right triangle here, where it is known as 90 degrees. Now this touches a bit into trigonometry, where, and again, the reason why I'm kind of covering all this is because to cover the unit circle isn't necessarily just to say, here's what's on the book. It's kind of to cover the things preceding it, so then you can kind of connect the dots on how these things work together. So, yeah, sure, I could just read the text, but I mean, that's what the class is for, right? If you're not quite understanding the unit circle and how it functions, I hope this helps a bit more. Or supplemental to what you're learning on the subject matter. So 90 degrees would be something like in a triangle with a right angle, and they kind of draw this little square thing to indicate it is 90 degrees. And these things can be like a bunch of funky shapes, right? They can look like that. Oh, that's a drawing. Like that. And it can look like that. But as long as these lines are perfectly straight, then this is still 90 degrees right here. Okay. Nice. Now, what changes, though, is the degrees on these sides. This is a smaller degree, this is a larger one. Maybe I should kind of draw it in a way that's more representative. This is a larger one, this is a smaller one, larger one, and then these are equal, right? And so similarly, with the unit circle, you have that 90 degrees, but then you also have a bit extra to it. You have something like 180 degrees, which is 90 plus 90. So for every of these quadrants, right? Is that what they still call them? I guess use the word terminal. Okay. Well, anyways. So you have 90 to go from here to here, then 180 to go flat. Whoops. Then 270 to keep her going. And then the extra last part is you add another 90, because that is the full rotation from one quadrant to another, and that is 360. And the reason why you get those numbers is because degrees is not quite it's not quite like temperature degrees. It's more like how things rotate. So, you know, this is maybe like, I don't know, 5 degrees. And this is like 15. I think here would be 45. This would be like 50. And it just kind of inches up and up and up. It's not quite like a straight line where it goes like this. It's kind of like a curve. And that's why they always draw it like a curve, because it's how things twist and move. So say for example, if you want to do a complete turn, right? A complete spin. You know, a spin is usually measured in something like a circular shape, because oh, does my model spin all the way around? No, it doesn't. But if it did, imagine spinning all the way around. Then they would call that 360 degrees, because it's not quite like a line. Imagine looking at something from the top, I guess. Right? If oh, here's a good example. Okay. Let's say, for example, you have a screw, right? And you have a screwdriver. I'm not really good at drawing a Phillips. Could I draw a flathead, maybe? Does that work? And they have this little divot, and they get fat. Yeah, okay. That's good enough. Alright, so you have a screwdriver, a flathead, and you have a screw that you gotta twist, right? And if you're looking from the top down at this thing, right? You're not looking at like the side. Well, hold on. I think these things have like a kind of a pointy end. Yeah, you're not really looking at it the side. If you're looking at it from the top down and you're seeing how this thing rotates, as you twist into it, there's two directions, right? There's there's lefty-loosey and there's righty-tighty, okay? So if you turn it clockwise to the right, that would tighten it. But if you imagine you're loosening the screw, right? And you're twisting it to the left. Because maybe you tightened it too tight, right? And you tightened it just a bit too tight, and you're worried that it might like break under it. You know, how much do you loosen this thing up? And so if you were to tighten it so that, let's say, for example, if you have this screw and it looks uniquely like this, right? There is a pointer right there on the spot. And they say, okay, nope, it's too tight. You got to loosen it to where it looks like this. Where this point looks there. Then you would loosen it 90 degrees. You're moving this point so that it turns and rotates. And can I do this? No, it only has like a move feature. It doesn't have a rotate feature. Yeah. Okay. So to go from here to here, you loosen 90 degrees. Because again, you can't like, when you talk about things that rotate, it's not so much like a line, it's not so much like an exact number on a graph. You know, you twist it. You twist it, you loosen it, as you can see. And that is a 90-degree loosen, turning it from one point to another. So, similarly, unit circles. Going back, you can imagine that you are loosening your x-axis, your line on the x-axis, right? You just have a point right here. And just like what you would do with the screwdriver, you loosen it 90 degrees, so then it points up here. So you kind of twist it, and it slowly moves all the way up. And that is how the unit circle kind of works. It's just this constant screw that you're kind of twisting from one direction to another. But then there's now math involved. So it's not as easy as like, you know, doing that. Alright. Now, if you were to kind of go more into the details, where you're going from 90 to 180 to 270 to 360, right? Then there's also more degrees you could kind of add, right? You could say, oh, maybe I could undo it like 720 degrees. How many times would I be turning this thing? And that'd be like 2 complete rotations. Because again, a lot of the math stuff that parallels to real life stuff is that there's like the practical example, which is loosening the screw, and then there's the math example. But the reason why is because, let's say for example, if you're building the thing that needs to be screwed in, right? If you know the size and the shape of the screw, and you're trying to create an object that requires some screws, you know, maybe you could just say you put it in, sure, but if you want it to be perfectly tight and not over tight and not under tight, and you know the exact shape and size and dimensions of the screw, and you know like all the details, right? You're trying to build this like furniture set. you're an IKEA guy, and you're making this own furniture set, and you can decide exactly the shape of the screw and how many there are, and then how many times to twist it. You know, to simplify it, you can say, yeah, you put in the screw, you push it in, and you rotate it and righty-tighty it about like 10 times, right? No more, no less. But before you do that, while you're prototyping, while you're figuring this thing out, maybe you would use something like, well, no, you'd probably use something different. I don't know. Maybe you'd actually practically like build the thing and then work with a prototype. You probably wouldn't use unit circles or radians. I'm sure we'll figure something out. I'm sure we'll figure out like a more practical way in which how to apply unit circles to real life. But point is that this is related. Because unit circles is used to kind of understand degrees. This is like the gold standard of degrees and radians and, you know, turning. Okay. Now let's see. I think this is enough for this part. I kind of want to see if there's I can touch on radians a bit. So let me find that. Oh, right. Actually doing math. I should do that. Alright, so yeah, you can actually apply a bit of math to this thing. Let's see if I can copy this. And here in this example, they kind of do basic algebra. Where they say, okay, how do I put it? It's not like, Okay. If you know division, right? And you've graduated from things like long division with like that, and you moved over onto things like fractions, right? Like that. It's taking that concept, and instead of just using simple numbers, they're basically doing the same thing, except they're adding this little circle symbol to it to make it degrees. Because it's the same kind of math, it's the same structure, you apply it in the same way, where you're doing division, but they just add the degree symbol and then they make it by tens, basically. So for here, to start with, they kind of gave the answer, dang it. Alright, so you have 30 degrees divided by 360 degrees, right? So then you kind of cross out the similar parts. Sorry, I shouldn't have. There we go. Alright, so you cross out the zeros, but then you could also cross out the degree symbols. And then you just have 3 divided by 360, and then that's 1 over 12. Yeah. Why would they do that, though? Ah, I see. Alright. Well, here, normally... what are they doing here? Sketch an angle of 360 in the standard position. Sketch an angle of negative 135 in the standard position. Oh. Okay. 1/12 equals 1/3 of a quarter, so I'm a quarter notation. We can sketch a line at 30 as so. Okay, so here what they're doing is they're trying to think about how do you sketch 30 degrees, right? And that's a pretty good idea. So if someone's just asking you to sketch 30 degrees neatly, and not just kind of eyeball it, and you don't have a ruler, that's going to be a little bit tricky. And so they kind of gave us a solution wherein, well, what exactly does 30 degrees mean in terms of like a shape, right? Although I think they could have just done like, well, no, this makes sense. The unit circle is a whole circle, right? The whole thing 360. So if you wanted to take a shortcut, they have you do it by 30 divided by 360, but I think, okay, well 30 is less than 90, so it's probably going to be somewhere over here. Then you could probably just do like 30 degrees divided by 90 degrees. That equals like 1/3. So then you realize, okay, since we know it's going to be somewhere in quadrant 1, and it's going to be 1/3 of the thing, then I just need to divvy this section up into 3 chunks. And I know that it's probably going to be, if you have like a 1 here, and a 1 here, on your thingy, then you could just kind of sketch out a nice little curve. Okay, it looks okay. And then you could just divide this into 3s. So it's not going to be like half like this. Sorry, it's not going to be half like this, because that would be 45. That'd be something like 45 degrees divided by 90 degrees equals 1/2. And then this is where you'd want it. Not quite that one. Instead, you're going to try to figure out a third. I don't think this really helps, though. Sometimes when it comes to math, it's not about eyeballing it and doing it right. Sometimes it's just about showing your work. So, yeah, sure. I could have just said, yeah, I know 30 degrees, but that's not for someone who's still learning and trying to show that their teacher, they know math. You still have to go through like the tedious steps of like doing it how they want, in the way they want it, to make it proper and correct. But I mean, again, if you change the way in which you think about math, it's not so much that you get graded on getting the right answer. You mostly get graded on showing your work. So, you know, even if you show your work and you get the wrong answer, then the teacher can kind of point out and say like, oh yeah, this is where you messed up. Whereas if you just have the answer and it's correct, they might not like it because then they can't like understand the steps or how you got there. Also, it makes them think that maybe there's some cheating involved. So yeah, that's the thing about math at school. It's mostly about showing your work, more so than getting the right answer. So yes, I'm taking a bit of a shortcut, and I shouldn't. I should do it in the way that they want it, which is 30 divided by 360 to make it 112, and then to say, okay, there's 4 quadrants, so then you take out the 1/4, because it's basically 1/3 of quadrant run, and that's what it is. Yeah, okay. Well, I guess that's that. Oh boy, but divide by 360. It makes sense. It makes sense why they would have this thing, because it covers all numbers, right? If you have any degree, it could be like this degree, or this degree, or this degree, or just 360 itself, right? If you divide by 360, then you can get a fraction with which you could kind of chop up the quadrant into. And then if you divide that by whatever this number is, split it into like 1/4, or some multiple of 4, I think you could figure out which quadrant it's in. But that's still weird. But that's okay. You know, as a bit of a tangent, sometimes when I help students with their homework, the way that they cover and they do math is a bit different than how it used to be done. Or it's very different. It's like never brute force math where you just, you know, kind of eyeball it and solve it. It's usually like some kind of overly complex way of doing the thing using new terms and using new methods that the student has never experienced before. And it feels, I don't know. I feel like that's where a lot of students get lost in the sauce, right? It's like Magic the Gathering keywords. Right? There's some evergreen keywords. Okay, sorry. A bit of a tangent ramble. But it's math related, I swear. Or at least it's school related, so then, you know, hopefully you can apply it to the way in which you conduct yourself in school to understand that may not just be you that's struggling. So in Magic the Gathering, there's like keywords like flying, right? And that makes sense where the creature has wings, it flies, and then it can only be blocked by flyers. Sure. And that is kind of an evergreen keyword that they use, and then you can put it on cards that are new, that are old, that are way beyond, and then it kind of makes sense. It's the way that everyone does it. And this is kind of like your X values, this is kind of your plus signs, this is your minus signs, this is your other stuff that, you know, people kind of understand that this is how you do math, right? But then sometimes there's like new keywords that's like unique for one set, and then they like have it like a like thingy. Thingamabob. And then there's all this kind of text about what it does, and it has like all these unique things, and it's like a whole paragraph, right? And these can be weird things, like maybe stuff like radians, things like limits, things like sine, right? These can be phrases in which you only experience for that one math class for that one semester, that don't really apply to other math classes or other stuff. And that can be kind of tricky. That's where I find that students kind of get lost in the sauce, where that they're learning these new terms and things, and they don't necessarily, like, they add upon the basics, yes. But they're also their entirely unique thing, and then this is the part where they say, well, why do I need to learn this? And so, again, going back to unit circles, the way in which maybe someone wants to do math, where they think, okay, well, you know, maybe I want you to sketch it out, maybe I want you to draw it, do something different, right? That kind of falls into this other category of, you know, how do we do a graph? Well, you know, there's this version of a graph, right? But then maybe they think, okay, well, here's another version of a graph that we could do which looks cool or different. I don't know. Yeah. This is one of those things where this makes sense and it works, but it feels like a one-off thing that is unique to this textbook and not necessarily to the greater teaching curriculum. So that way that this is less helpful than it could be if it was more generic, if it was more bland, if it was more evergreen. But okay. Dividing by 360. Sure. We divide 135 by 360, we get negative 3 over 8. We separate out the 1/4 so that we could figure out what quadrant it's in. And then, yeah. That's a very unique and specific way in which you're kind of doing degrees and stuff. That is not brute force, that is not very simple. That can be a little hard to follow. Okay. Well, there it is. There's that. Sorry, I didn't mean to go into a tangent, slightly critiquing this free and very helpful textbook that I'm using, but again, I'm trying to look for more of this simple, evergreen kind of math stuff that that is where the meat and potatoes are. Whereas some of this dividing by 360, maybe that's the way it's done, sure, but it seems very niche when you could just probably like eyeball it, or I guess use a ruler. Okay, I'll move on. Oh yeah, okay, oh hey. Here's the thing though, right? One of the things I like about the books is it also agrees with me. Dividing a circle into 360 parts is an arbitrary choice. Yes, just like how we have the Celsius like 0 to 100. I mean, it's not necessarily arbitrary that it goes from, like, you know, freezing to boiling, but the fact that we use the number 100 itself is just because, you know, the number 100 is cool and easy to remember, right? Similarly, the number 360, again, it's not the fact that it is a circle where you start from, you know, a starting point and then you go in the whole way around. You know, that's an important way to measure, but the numbers that we use specifically for 360 is a bit arbitrary. Okay, cool. Never mind. I like this book. It has some good stuff. Okay. Let's see. 2 pi r. Yeah, okay. I remember this. This sounds familiar. Now let's see if I could... Okay, get a screenshot of this area. That's not correct. Oh, jeez. Okay. Pardon me while I try to figure out how to screenshot this thing very carefully. Copy. And paste. There it is. Oh. Alright. So radian is the measure of the central angle of a circle that intercepts an arc. Let's see. 2 radii because the total circumference equals 2 radii. Full rotation is 2 radians. Okay, yeah. So basically, if you cut this thing in half, right? If you have a circle that like cuts it perfectly in half, just the most excellent slice, right? This rotation is basically 1 radian. And then this other slice is another radian. And so that's why they say you have 2 radians as a full thing. Now as for why a radian isn't just the whole rotation and just like a half rotation that like cuts in half, I wonder why. Is it because people like slicing up like apples or something? No, I don't know. Again, I'm sure there's some fascinating history for that. But I guess the way to remember is that is there kind of like a shortcut, like a PEMDAS sort of thing, for memorizing that a unit circle is 2 radians and not just 1 radian? That's a good question. I don't know. If anyone has any ideas as to why, or kind of memorized little formulas, why a unit circle is 2 radians and not just 1 radian, yeah, please say so. That'd be interesting. I guess it's just kind of one of those things you have to remember. Like, this is what it is, right? Sort of like how when you multiply by an exponent, something squared is just it times itself. I guess you just have to kind of remember that a circle is circumference is 2 radians, not just 1 radian. Okay. Cool. You know what? I wonder if it's based off a sunset. And someone says like, yeah, that looks cool. That looks rad. That looks rad. It should be a radian. Yeah, the sunset is rad. And so if you have a full sun, that's 2 radians. Yeah, maybe that could be something. Alright. Yeah, I don't know why the unit circle is just 2 radians. Okay. Let's see. When an angle is described without a specific unit, it refers to a radian measure. 3 radians. In fact, a radian is dimensionless, since it's equal to... Okay, yeah. So, I guess radian is just kind of like their, x value? Really? It refers to a radian measure. Yeah, so, when you have a distance, and you don't know how far it is, you say like, it's like however many miles away. It's x miles, right? If you have to twist on a screw, and you don't know how much you have to twist it, you're like, you just turn it so many times. You turn it a radian number of times, I guess. Interesting. Okay. Yeah, so this is 1 radian. Arc lengths. Sorry, I'm kind of just reading as I'm talking. So there's going to be periods of like silence. Although, you know what? Maybe I should just read out loud. I think that'd be helpful. Ooh, I only have 10 minutes left. Okay, an arc length is the length of the curve along the arc. Circumference, ratio to the radius. Arc length, angle, constant relation to the radius. Regardless, length. Radian measure. Same. Regardless, radius. Depends only on the angle. Okay. If S equals R, then theta equals R divided by R equals 1 radian. Now, the nice thing about unit circles is that this is the part of math that I think is the most visually based. Like, sometimes when you have something like algebra, where it's all just kind of like numbers and words, you know, it can be a little difficult to follow along for someone who's maybe more visual than instruction based. But thankfully, with unit circles, there's a lot of pictures. Again, maybe not on like a test or something, or a quiz. Maybe they just might have like word problems, because you have to kind of understand not just you have to understand the concept with the words without the visuals, but then you also have to understand the visuals without the words. And so I think unit circle and this level of trigonometry, you kind of get a best of both worlds, where you kind of have visuals and words to kind of understand a concept more completely. Which is lovely. Okay, so looking at this thing, I think it's just kind of describing the concepts, which is very nice. Sometimes when I describe the concepts, it's a bit scattered brain and kind of calling back to older things, but here it's something completely new, and it's on its own. Okay. So if we have a radian of unknown measure, right, and it's just kind of here, and it is of this, is it arc length? Yeah. This arc length. Let me see if I could bring up the screw example again. So you got a screw that's pointing like this, and you want to loosen it, right? But you've already loosened it a bit, because it used to be facing this way. And so now you loosen it a little bit, and it kind of goes like this. So what it once was here, it goes up to here, right? Just some generic distance. But it still feels a little too tight, and you don't want to overshoot it. So then you want to loosen it just the exact same amount, right? So you're not going to go like all the way over here. That'd be nuts. No, instead what you're going to do is you're going to do it just a little bit more like that. And in that example, this is basically the 2 radians, where your screw loosening what initially started from the starting point, you now done just a little bit, but the same amount of a little bit, exactly the same, twice. 2 radians. 1 radian, 1 twist, 2 radians, 2 twists, total. And so that's kind of what they're showing here, where an unknown degree, you twisted it once, and then now you have it twice. And then you can just kind of keep going. You can go all the way through the unit circle, right? And so this is kind of more like a math visual graph of that revolution, where you go from the starting point of being flush, or 0, like completely tight, to doing it Oh, that was a poor example of drawing. Yeah, it's about there. To doing it again, and they could do it 3 times, 4 times, 5, 6, and then a full revolution. Okay, that's kind of neat. Now, is there ever an example where someone would look at the screw that you just undid and critique your work and say, yeah, I see you've twisted it a radian. Let's do it 2 radians. Just do it the exact same amount, but a little bit more. I don't know. Who knows, right? It's kind of more just like, do it as you feel, rather than exact calculations. But hey, looks like it works. Alright. Now, moving on to this next one. Ooh. Consider on this side 2 circles with radius 2 and then with radius 3. Okay. Okay. I think I understand. Could be wrong. But what they're basically saying is that if the smaller has a... Yeah. So basically, if you have this smaller screw and a larger screw, right? And you're doing the exact same process, where you have it at first like this, completely facing one way, and then you turn it so that now it is in this direction. Whoops. Ah, that's right, it's not a straight line. It's like this. Not quite 45 degrees, a little bit more. I'm gonna do it like that. There we go. Alright, so you were starting from this point and then you turn it 1 radian, right? Even though this is the larger screw and here you have a smaller one, you both turn them the exact same degree. That's basically what it says. And so they both equal the same radians. They both equal the same degree. So let's say, for example, if you if this first radian that you turned it was something like I don't know, 60. Well, yeah, let's say 60. Right, you turn this thing 60 degrees, so just a little bit higher. I know, let's do a weird number. Let's do like 53. Alright, you turn this thing 53 degrees, and you turn the screw 1 radian, and then you do another 53 degrees, and that is 106 degrees, right? And then you have this larger screw. Well, because they're both basically the same circle shape, if you want to loosen it the exact same amount, then you would still turn it the first time 53 degrees, and then if you want to turn it again, then it'd be like 106. And then that would, let me draw that one out. Because a circle is a circle, no matter how big and small it is. It doesn't depend on the size of the circle itself, but rather how it twists and turns. I'm sure there's a joke there somewhere, but right now I'm too focused on doing math. Let's see, 106 degrees. Okay, so that's the nice thing about radians. And unit circles and degrees and that, you know, it could be big, it could be small, whatever. But the rotation and the degree usually kind of lines up no matter how it is. So if it's like literally doubled, it's still the same degrees. And then they do a little bit of math here to kind of show that. Oh, jeez. I wanted to get to more. Okay, well maybe next week will be a part 2. But for now, that's kind of all the time for now on unit circles. Yeah. Alright, and there it is. So until next week, I guess I'll try to continue with this on a bit with unit circles. And again, if anyone has any math that they want to talk about, need help with, if you've been if you've been procrastinating and you're like, man, I really need help, and somehow Twitch is the place where you decide to procrastinate and you stumble upon this, hey, maybe I'm your guy. Maybe I can help you out with some tutoring. Alright, but until then, thank you for anyone who came by, and I'll see you all next week. Have a good one.